If you place a single isolated charge in a void, the electric field it radiates is stable. It pushes outward with total, unchanging symmetry. The defining rule of this classic static field is that it is conservative. If you force a test charge to move through this field in a complete circle, returning to where it started, the net work required is zero. The forces balance perfectly. But this balance breaks the moment we introduce a changing magnetic field. This fluctuating magnetic environment generates a different electric field, one governed by rules that do not apply to static charges. Understanding this induction requires mapping the behavior of this non-conservative field, where the work done depends on the path taken through space. Consider a charged particle forced along a circular ring, directly inside a magnetic field that is actively changing over time. Completing this circle yields net work, calculated as charge Q times the induced electromotive force, psi. Energy is pumped into the system. The engine explaining this is Faraday's law. The electric field line integral around a loop is proportional to the changing magnetic flux. Our challenge is to take this equation and use it to deduce the exact strength of the induced electric field at any distance from the center. We are deriving the very mechanism that allows generators and transformers to power modern infrastructure. We define the physical space, a circular region of radius r. Inside, a uniform magnetic field is actively growing in intensity. That rate of change is linear. The magnetic field strength B at any given moment is a constant B sub 0 multiplied by time, t. To map the induced electric field, we establish an observation point at a distance r, measured outward from the center. Calculating the strength of this field requires analyzing two regions, the space within the magnetic boundary and the empty space beyond it. It is a geometric balancing act. We are tracking whether the area of the magnetic flux, or the perimeter of our observation loop, expands faster. This diagram shows our first scenario. Observation distance r is less than boundary r. The path integral on the left simplifies to electric field E times circumference 2 pi r. On the right, enclosed magnetic flux is B0 pi r squared t. Taking the time derivative removes t. Equating perimeter with this flux derivative solves for E, a field strength of negative B0 times r over 2. Moving outward, the electric field gets steadily stronger. The expanding area of enclosed magnetic energy outpaces the linear growth of the loop's perimeter. Now, observation distance r extends beyond magnetic boundary r. The path integral on the left remains unchanged as 2 pi r, but magnetic flux on the right is capped at maximum area pi r squared. Taking the time derivative, r squared acts as a fixed constant. We equate the expanding perimeter with this capped flux derivative to solve for the exterior field, negative b sub 0 r squared over 2r. Outside the magnetic zone, the field weakens. The magnetic engine has reached its maximum size, and its fixed energy is stretched over a massive perimeter. This graph plots the electric field magnitude against distance from the center, fusing both zones into a single spatial profile. Inside the magnetic region, the field climbs linearly, starting at 0 and gaining strength moving outward. The point of maximum intensity occurs exactly on the boundary of the magnetic region, where r equals r. Stepping past that boundary, the field drops on an inverse curve, decaying as it radiates outward toward infinity. Mapped onto physical space, the electric field vectors form concentric spirals. They grow powerful until they hit the perimeter of the active magnetic region, and then they shrink away into the void. This sprawling, balanced structure is the signature of a non-conservative field. It exists because a fluctuating magnetic environment constantly forces energy into the surrounding space.